So in the last video, we discussed density and pressure, especially pressure at a certain depth in a liquid. So the outcome of that formula is, here is an example. I have a pretty complicated liquid container. So we have a straight section, we have this windy section, there's also this section with a bulb, and there's a slanted section and another straight section that has a larger area. So what if we fill this thing with water and just keep the bottom level? Where does the water level go? So assume that the water level goes over here at this section. Okay, even if the shape of the tube is different, it's not even straight, the water level seems to maintain itself across all the different sizes, shapes, and maybe tilt. So that is an outcome. This is water, and that is an outcome of the pressure in equilibrium. Because if pressure is in equilibrium, then liquid does not actually flow. And if there were any change of pressure, liquid would flow. So what this means is, if you start from this surface, here's pressure P0, which is an atmospheric pressure. Not necessarily 1 atmosphere, but an atmospheric pressure. So at a certain depth, if you go from this point down, the depth acts as y. So at a certain depth here, the pressure will be P0 plus rho g y. Y is positive pointing down. And that is the same across the entire container. What if they're not the same? Well, if they're not the same, for example, at this point pressure is somehow higher than at this point across the same height, then liquid over here will tend to flow. It will actually flow from the higher pressure to the lower pressure because higher pressure represents higher amount of force. So the liquid will flow and eventually it will equalize itself again. So if you have static liquid, then you should have this outcome that the liquid surface at every point is the same exact height. Okay, so what if we have liquid here? So this is just a simple beaker. So we have liquid here, and what we want is we want to just use that formula again. So we set up this point, which is P0, and at the moment it is the same as atmospheric pressure, and this points down. Y comes down. So an arbitrary depth here with a axis y here, we have pressure Py at this point, and Py is equal to P0 plus rho gy. Okay, so what if we start applying force against this surface? Say we seal it off with a piston and we start pushing down with a force, this force F, and the piston has an area of A. So we have basically increased pressure by this delta P, which is equal to F over A. Alright, so that changes things. That changes where how much pressure this interface has. It used to have just P atmosphere. Now it has this added pressure, delta P, due to the applied force. And at this depth, the pressure is still equal to P0 plus that, except that P0 has increased from the just atmospheric pressure to that delta. So we'll add that delta to the end. So essentially everywhere, this is an arbitrary location. So that means everywhere in the liquid, the increase of pressure is felt uniformly. So if you apply an additional pressure to the top surface, everywhere, every depth feels the same exact added pressure due to that force over the area. Alright, so that is called Pascal's Law. So it has a lot of applications, especially in hydraulics. So let's look at the top right diagram here. So we have two different cross-sectional areas. So this area A1 is small. So we'll fill it with liquid. Same level. And this side A2 is large. Could be much larger because we're only looking at the cross-sectional. This could be a diameter. And then if you square that to get area, you could get much larger area on the A2 than the A1. And then we suppose we apply a force F1 against the left surface. We could be putting a piston here, just applying a force against the piston. Then the liquid level at this other location will rise, right? In order for that to not rise, we'll have to apply another force, a different amount of force, F2, to hold it. So this side could be the hydraulics pump to push the liquid with a hydraulic line, and this other side could be the hydraulic lift. It has a large weight on it, such as a vehicle. You want to lift the vehicle up to do maintenance or inspection under the vehicle. So there's got to be a force there here already. The force from the car pushing down due to gravity, and then you want to lift it up, so you balance that force. So according to the Pascal's principle or Pascal's law, the added pressure due to the push will be the same across the same height, same depths, or everywhere. So we'll do this. The delta P on the left side, the delta P here is equal to F1 over area 1 because we're pushing. And here, delta P is equal to F2 over A2. According to Pascal's principle, these two delta P's are the same. So we have F1 over A1 equals F2 over A2. So the conclusion is F2 on the other side is A2 over A1 times F1. So F2 gets amplified from F1, and if A2 is much greater than A1, then we get F2 much greater than F1. So we basically amplify our force by applying the force at this smaller cross-sectional area. Then the amplified force, the much larger force, appears on the larger area. So this seems to be very good, but there is a catch on the other hand. So let's look at how much work we can do with these two forces. So let's look at the left side first. We push with this force F1, so let's assume that we push down and we squeeze down this much liquid. So the amount of liquid squeezed out is Y1. And this other side will rise, but because of the larger area, the rise is much less than the drop Y1. So this small quantity is Y2. And let's assume that this liquid is incompressible. So we're going to assume that the change of volume here, the volume pushed down, is the same as volumes rising up. So let's calculate how much work is done by the force on the left side. So work done by force 1 is F1 sustained over a displacement of Y1. And the right side, work received is 2, that's F2, Y2. And we also know the volume, this volume here, that's the delta V1, this teeny amount, delta V2. So delta V1 is equal to A1 cross-sectional area times Y1 height, and delta V2 is A2 times Y2. Because the incompressible liquid assumption, so liquid is incompressible. In practice, this may not be exact, but it should be pretty close. So incompressible, so we have delta V1 equals delta V2. So we have, as a result, A1 Y1 equals A2 Y2. So Y2 is equal to A1 over A2 Y1. And if we plug this into the work equation here, so W2 is equal to F2 A1 over A2 Y2. And because how F2 and F1 are related here, so we can plug this in, we get A2 over A1, A1 over A2, F1 Y1. So I think this is typo, that should be a 1. So we divide all these out, and it seems like work 2 is the same as work 1, right? So we conclude this is the same as work 1. So the work does not get amplified. We still have energy conservation. Even if there's no friction, we're not amplifying energy. We're amplifying forces. So if we cannot apply a large enough force, we can use this to apply a large enough force, except that we have to do more displacement in order to for that large force to do the same amount of work as we do with a smaller force. Thanks.